is continuing to talk about the least squares regression line. So we know that's like our line of best fit. We're trying to write an equation for a line that fits our data the best. And there is a method for that. We did it by hand, but it's easier to do it on the calculator since we get a lot of our information from that anyway. We've also talked about how to decide if data is linear. Not yesterday, but the day before. What were we looking at to decide if things were linear or not? That chart. We had our correlation coefficient, the R, and then we compared it to table 2 with our critical values. And so if the absolute value of R was greater than the number in the table, then it was enough to be considered linear. Otherwise, it was not. And why did we have to do absolute value when we looked at those? R can be positive or negative. What does a negative mean? Yeah, it's just a decreasing line. So that's why we had to always just consider the positive. All right. So the final piece with this is what's called the coefficient of determination. This value is R squared. So the same as our correlation coefficient, that's our R. If we square that, we get the coefficient of determination. And what it does is it tells us the proportion of the variation in the response that is explained by the least squares regression line. So if we're looking at data, okay, we've had several different tables. Our y values are different, right? When x is different, we get a different y. So part of that is to be expected. If you are a point on the line, every single y value is not the same. So the R squared is basically accounting for that. What percent of the differences in the y is just because these points fall on the line, and on the line every y value is different. And then if it's not accounted for by the line, it's some outside thing, because we know when we're looking at these regression lines, they're not a perfect match. We have points that don't fall on those lines. So if you are looking at a square, we know we're going to get a positive number. It'll be between 0 and 1, because our correlation coefficient R was between -1 and 1. And it's just like a percent. So if you get 0.95, that's 95% of the variability is because of the line. 5% would be something else. If your R squared is 0, that means the line is a very poor fit. That would be like saying nothing is explained by the line. The line doesn't work at all. R squared equals 1 means every single point falls on that line, so 100% of the difference is because the point is on the line. So ideally, we are looking for the closer we can get to 1, which is kind of like what we look at with coefficient of determination. We said positive and -1 are perfect relationships. The closer we were to 0, the worse it was. So it's kind of the same idea. With this, we are comparing deviation, or how things differ from the mean. So explained deviation is just the differences that are explained by the line. We are expecting some variation. We are looking at a lot of different points. We expect them to be different. That R squared is giving us our explained deviation. How much of those differences is accounted for by the fact that they fall on the line? The unexplained would be any other factors. So not by the line, just because we have a poor set of data or something like that. We are really going to do this solely from our calculator today. So we're going to talk about how to find that, kind of what that means in terms of our graph. So we'll start with an example. So I want to find the coefficient of determination for this data. And this is the same example we've done before, but obviously it's a new day, so we have to put it in our calculator again. once we have our data entered, where did we go to get the R value before? Same thing we did when we did our regression line. So this gives us the equation of our line. The R is what we looked at that first day, the correlation coefficient. R squared is what you get when you just square this number. So that is our coefficient of determination. So 0.5973. Okay, what that means is 59.73% of the variation in drill time is explained by the regression line. Okay, so that means the other 40% is due to something else. So our line is not perfect. It only accounts for almost 60% of the variations in our Y. In terms of the line of best fit, kind of the same thing that we talked about before. If you have a really high R value, then it's almost perfect, so all your points are going to be very, very close to your line. As this R squared gets smaller, what do you think is going to happen to our points? Further away. So this is just an example to illustrate a few different data sets. So in the first one, the R squared is 0.9999, and you can see it is almost perfect. This one, your R squared is 0.947, and this one does a very poor job of describing our data, and that one is 9.4. So as your R squared gets smaller, it just means our data is more spread out. The second piece that we're looking at here is residuals. And just like everything else, guys, these are all on the formula sheet. So we talked about residuals yesterday. And what was a residual? Right. The observed minus the predicted. So what really happened minus what we got when we use our line. And the idea of the regression line is to make all the residuals as small as possible. Right? We want them to be a close match to one another. Well, residuals also have some other purposes, and we can use these to help decide if our data is linear or not. So we have a couple different tools for that now. The R value, if we want to compare it to our table, or we can look at residuals. It can also tell us if there's any patterns going on in our data, like maybe our regression line is really, really good when X is small, but as X gets bigger, our regression line is not as good. And it can show us that. It can also help us find outliers. So to do this, we are going to look at a residual plot. The goal, so if we have good data, then the residual plot will have no pattern at all. Okay, a residual plot is essentially if we went through and found the residual for every single point, the value that we had minus the value if we used the line, and we plotted those numbers. If we have good linear data, we would expect some of our points to be higher, some of our points to be lower, right? So we should just have random points. If we see a pattern with that, then we have a problem. The reason we do this is the correlation coefficient can show there is a linear relationship when there actually is not. residuals check for this. So it's possible that we might get an R value that our table says is good enough to call it linear, but if we actually dig a little deeper, linear is not the best option for that data. So that's when you would want to look at residuals to see if there's something else. So let's look at just a couple of examples of what a residual plot. So this is a good set of data. We have the points are all spread out. We have some above, some below. This one is bad because you can see all the early x values, the observed was higher than we predicted. In the middle, all of these points in the middle, the observed value was lower, and then it was higher again. So there's a pattern. If you have a pattern like that, that means it's a linear model is not the best option. So let's look at this one. So we are going to determine if this is linear data. So we're going to enter all of this into our calculator. So let's do a couple things first. Let's look at the scatter plot of that. So turn it on, X is L1, Y is L2. If we go to zoom 9, does this look linear? Yeah, it does. Okay, let's look at the R value. Okay, so if we do that, we go to stat, calculate number 4. All right, and if I do this, it gives me a regression line. If I look at my R, negative 0.9941, does that seem like it would be linear? It's telling us a pretty strong negative relationship. R squared, 98.8% of the difference in my y's is accounted for by the line. So all this looks extremely promising. Okay, what I want to do now is look at the residuals. So residuals would be if I went through every one of these, plugged my x into my equation, got that y value, and subtracted the y value from the table and the one I got from my line. There is a faster way to do that on your calculator. If you go back into your stat plot, okay, I still want a scatter plot. My x is still going to be L1. For your y's, if you hit second stat, it gives us a list of common things. And we actually want number 7. Those are the residuals. Your calculator will find all those residuals for you. Now, if you're going to do that, you have to first run the linear regression. So going in and doing the number 4 so it gets the equation of the line. If you don't do that and you try to graph the residuals, you're going to get an error message because your calculator hasn't written an equation of a line, so it can't find the residuals yet. So now if I look at this, let's go zoom number 9. What do you see about these residuals? There is a pattern. And we said if it's a good line, there would be no pattern. So everything looked like it was a linear relationship, but this is telling me my line isn't great. It's an overestimate at the beginning, an underestimate in the middle, and then an over again. So there's a pattern. So this is not linear. Even though everything else said it should be, the residuals say it's not. Okay, it doesn't mean the line still didn't do a decent job. It just means there's probably something better out there. So the reason so if you're looking at the residuals, a pattern is bad. You want just random points, no pattern at all. Did everybody get that on their calculator? So there's really 3 problems we can have with residuals. The first one is what we just saw, if there's a pattern like this. The second one is what's called constant error variance. If you are looking at your residual and it gets wider or it shrinks over time. So if you're looking at it and you're getting a cone shape, that's bad. That means your line was a pretty good estimate at the beginning, but as my X went on, what happened? They got further away from the true value. So as time went on, it became a worse approximation. So this one is not ideal. So that's the second problem we might see. The third thing is outliers. And an outlier doesn't necessarily mean that it's not linear, but it means there's some points that probably skewed our line because we know R is not resistant. So if you have an outlier, it's going to throw off everything. If we look, this is the original scatter plot, so you can kind of see there's an outlier. If you look at the residual plot, all the points are next to each other except this one way out here. So residual plot is just another way of checking for outliers. And we also know mathematically we can do it when we do the upper and lower fence. We can find outliers that way as well. So, oh shoot, I should have had you do this before we cleared that data out. Sorry. I need to change the order of my examples on this. I wanted to do a residual plot for our drilling data and see. That one didn't have a very high R squared value, did it? So let's see what that does. So just for fun, let's put it back. So a couple things. Before you could do this, you need to run your linear regression just so your calculator will have that equation in memory. Then we can go into our stat plot. You probably have it all set from our last example, but we want the scatter plot, and your Y should be your residuals. And if you go zoom number 9, okay, does this one have an obvious pattern or an outlier? No, but which violation does it have? The constant error variance. You can see it's a pretty decent model off the bat, but as time goes on, it's becoming less accurate. So it violates the constant error variance. Now, there is a little bit of subjectivity here. You know, is this a horrible violation? Is it super obvious? No. So the linear model, it's not horrible here, but it's not great. And we kind of already knew that because our R was fairly low there. All right, last, just a definition. Influential observation is any point that would significantly change the regression line or the correlation coefficient. So anything that's going to cause drastic change, that's typically an outlier. If I look at this one, do you think this first point, is it an outlier, first of all? Definitely. Okay, now the second question is, yeah, it's going to change our line some, but is it going to have a huge impact? And you know, one way to check it would be if we had the actual points, run the regression line with and without, and compare, did those lines shift a lot? The other thing we can look at, you know, this line would be increasing. So yeah, this point is higher than the others, but did it kind of follow the trend going up over time? Yeah, so it's going to change the line some, but is it going to be a massive change? Probably not, because it's following the pattern. Okay, case 2. Is this one a problem? No, that's probably the least influential of all of them, because if we were looking at our line, If you just keep going, that point is on the line. So that one is not a problem at all. What about this last one? Is it an outlier? Would it be a problem? Yeah, it's going to significantly change that line because it wasn't just increasing along with the trend. This one dropped way down, so it's going to significantly drop my line down. So in this case, this one would be the most influential. Case 2, that one wouldn't be influential at all. The first one, somewhat, but not a drastic change. All right, so let's go back to our drilling data, and let's add in a point. So if I had another 300 feet and 12.49 minutes, is that influential? Let's do this first. If we want to see if it's influential, we could do a couple different things. Let's look at the original scatter plot. So I'm going to change this back to my Y, make it list 2. Okay, so here's my scatter plot. And then if we ran our regression, right? Remember yesterday how we could add those to our calculator, our lines of best fit? So I need to go back in because I didn't write it down the first time. So one thing you could do if you're trying to decide if this is influential, we could just look at it and see if it's an outlier, and we can do that from the residual. Or we could look at this graph. So if I graph that line, there's my current line of best fit. We did that yesterday. So now let's put our new point in and see. So if I go back to my list, and I want to go to the end, and my X was 300. My Y is 12.49. Let's get our new equation from that. So here's the new linear equation. If you want a visual, you could always graph that. And so we can see there's the original, the blue one, the red one's my new one. Did that look influential? Yeah, it really changed the line. So you could have just looked at the residuals, checked to see if it was an outlier, but I think it's a little more obvious if we actually look. What does that new point do to our regression line? Does it significantly change it? And it did, so it was influential. Questions? So here is the game plan. I am done with this section, so I'm going to go ahead and give you homework. I will probably not collect this homework until Friday, especially given that we have several people out today. It'll be due Friday, so tomorrow you can work on it. I'm also going to give you the study guides for our next test. So we'll have tomorrow, Friday will be 20-minute class period, so we'll only have a little bit of time in here, but then I want this assignment done Friday and the study guide completed on Monday, so we can review Monday and test next Tuesday. Okay. Yeah. So review Tuesday, test Wednesday.